All right, today we're going to crack open a really foundational moment in quantum computing history. We're talking about an algorithm that was one of the first to really prove, that quantum machines could tackle certain problems in a way that regular computers just can't. This is Simon's algorithm. And to get why it's so powerful, we first have to understand the super clever problem it was built to solve. So it all kicks off with this central question, a real mind-bender. How on earth can a quantum computer find a hidden, secret pattern exponentially? We're talking billions of times faster than any supercomputer we have today. I know, it sounds like science fiction, but this is the exact challenge that Simon's algorithm was designed to absolutely crush. To really wrap our heads around this, let's think about it like a mystery. Imagine you've got this special digital lockbox. The puzzle isn't really what's inside, it's about the bizarre way the keys work. And this right here is the heart of what's known as Simon's problem. Okay, so here's the deal with this lockbox. It's been programmed with a secret binary string, a series of ones and zeros we'll call S. Now, you can stick in any key, let's call it X, and you get an output. But here's the twist. If you happen to find a different key, Y, that gives you the exact same output, it's a guarantee that those two keys are related by that secret string S. Your mission, should you choose to accept it, is to find that secret string S.
So, faced with this puzzle, how would a normal computer, what we call a classical computer, try to crack this code? Well, it doesn't have any fancy tricks up its sleeve. It has to resort to a clumsy, slow, brute force heist.
Yeah, it's pretty much exactly what it sounds like. The computer just starts trying keys, one by one, after another, after another. It stores every single result and just keeps going, hoping, just praying, that it'll stumble upon two different keys that spit out the same output. It's basically a random, incredibly inefficient guessing game.
And this slide just perfectly lays out the difference. As that secret string S gets longer, the time a classical computer needs to find it just explodes. It grows exponentially. It quickly becomes completely impossible. But the quantum approach, it scales linearly. And look, this isn't just a little bit faster. It's a whole different universe of speed. It's the difference between waiting a few minutes for your answer and waiting longer than the age of the known universe. No joke.
So how in the world does the quantum computer pull off this incredible feat? Well, it doesn't bother with single keys. It uses something you could call a quantum superkey.
Here's the basic game plan. First, using this wild quantum property called superposition, the computer creates a state that represents all possible keys at the exact same time. It's like having a master key that is every single key, all at once. Then, in one single operation, it queries the lockbox with all of them. After that, the real magic happens. Quantum interference kicks in. Think of it like noise-canceling headphones for possibilities. All the pathways that don't lead to useful information just cancel each other out. And when we finally measure the system, we don't get the final answer, but we get one heck of a powerful clue.
And this is a really important point. The algorithm isn't a magic 8-ball that just gives you the answer. It's more like a master detective, gathering and interpreting clues to solve the case.
So let's be super clear here. Running this algorithm one time won't just hand you the secret string S on a silver platter. That'd be way too easy. The quantum world is all about probability. What it gives you instead is a piece of information about S that you could never get classically without an impossible amount of work.
Every time we run the algorithm, we get a new clue. It's another string of ones and zeros we'll call Z. Now this clue Z has a very special mathematical relationship with our secret string S. And here's the cool part. Each clue you get essentially acts like a filter. It tells you something about S. And in fact, each valid clue you find rules out half of all the remaining possibilities for what S could be.
So what do? You run it again, get a second clue. Run it again, get a third. After just a handful of these runs, you've collected enough unique clues. You put them all together, and it's like a system of equations. You can just cross-reference them and figure out the one and only one value for S that satisfies all the clues. And just like that, the mystery is solved.
Okay, so this is a super clever solution to a pretty abstract problem. But why does it matter so much? Why is it such a big deal? Because it was a historic landmark. It was a massive signpost pointing to the unbelievable potential of quantum computers. And this is the real takeaway. Before this algorithm came along in 1994, the idea of a quantum computer being exponentially faster was mostly just theory. Daniel Simon's work was the first concrete, provable example of a quantum algorithm solving a problem exponentially faster than any classical algorithm ever could. This was the shot heard around the computing world.
So let's just boil it down. Why is this so important? First, it proved that the whole idea of exponential quantum speedup was real. It wasn't just a dream.
Second, it was a beautiful demonstration of how you can harness weird quantum effects like interference to pull hidden information out of a system. And finally, the techniques and ideas it introduced directly paved the way for even more famous algorithms, like Shor's algorithm for factoring, the one that has the potential to break most of modern cryptography.
At its core, Simon's algorithm is a tool for finding a specific kind of hidden pattern. And that just leaves us with this huge, fascinating question to think about. When you look at fields like materials science, medicine, or modeling incredibly complex systems, what other profound, world-changing secrets are just sitting out there, waiting for the right quantum key to finally come along and unlock them?